actually are able to receive such type of binary information. And first implementation or exemplary implementation of such protocol is called Practical Byzantine Fault Tolerant Protocol, or PBFT, which is a very known protocol in the space. But of course, the main disadvantage of it is the aspects of scalability, meaning that actually it was only scalable to a smaller number of peers. And if you know these peers in advance, you design the system in such a way, it was providing very good throughput properties and latency to the peers in the system. And it also had a very important feature that is so-called deterministic consensus, meaning that after you run these runs of communication that we will see on the next slide, the update is final, meaning that you can no longer modify it, which of course is a very nice property. And when we look at the current states of the blockchains, they are trying to provide also the aspect of this determinism. But still, the challenge that was introduced by PBFT was the aspect of scaling to large number of peers. And the reason for that is mainly the following. As you can see from the figure, it's very communicationally expensive. So you basically have to propagate the messages to everyone. They have to come back to you, and you are basically having these multiple phases of rounds that basically are ensuring that after these 3 rounds of communication, you basically are in the stage where everyone agrees that this is the latest state, and we can proceed further. Which is, if you can imagine, if you do it maybe between 10 people or 10 nodes, it's fine. 100 nodes start to be a bit tricky, and if you talk about thousands of nodes, of course, this doesn't scale very well due to the high message complexity. And therefore, basically, the main innovation of Bitcoin was how do we, just a second, there is some, yeah, perfect. Okay, yeah, now I think it's synchronized, perfect. And this, from my point of view, was the main innovation of Satoshi Nakamoto, who introduced the Bitcoin paper, that basically is allowing to achieve scalability and permissionless setting for blockchains, for peer-to-peer systems on a large scale. And the way how they have done it is, as I was talking before, is that instead of having deterministic reach of the finality of the consensus after this individual round, they change the view a little bit, and they consider actually another aspect of probabilistic finality, meaning that we are gaining confidence with more and more information that are being sent in the system, called blocks, and we assume that after certain information are aligned, basically all of the peers in the system will eventually have the same view, which basically allows us to scale to large number of peers, because we don't have to do this expensive communication rounds among all of us, but we just have basically centralized, or not centralized, sorry, but we have a peer that is propagating the block, is proposing the block, and it doesn't have to wait for the responses from everyone else, but it's just basically later on building on the view of itself. And the way how this block proposer is selected is using so-called proof of work, meaning that I'm running a lottery. I try to basically find the hash that will have certain number of leading zeros, and once I'm able to find it, I'm basically able to propagate the information that, hey, this is the next block we should be voting on, and here is my proof that actually I was able to calculate the corresponding hash. And the very important property is this asymmetric property, where finding such hash is very difficult, but anyone can very easily verify it. So that way you only have to do theoretically the proof of work once, but anyone can later on verify it without any major issues. And then after you find such value, you basically just propagate this block to everyone else, and they are able to verify the content inside of the blocks and make sure that everything is valid. And they are appending it to their blocks for the future. And again, for the next block, basically this process is being repeated again and again and again to make sure that the blockchain itself will be growing as expected. And as mentioned, these information are public, meaning that all of the peers in the system actually can see what information were propagated, and it's fully transparent to the audience. And the question that I think it's interesting to ask, what happens if actually there are multiple proposers? Because it's possible that I'm solving the proof of work problem, maybe some of you are also solving it, and we both find the right proof at the same time. And for that, in the context of blockchain, we talk about so-called soft forking, meaning actually that you will propagate the block, I'll propagate the block, but we will eventually have to reach some form of stability on the view we have. And this is usually done by the fact of calculating certain weight on a so-called longest chain, or basically by appending these individual blocks on top of each other, and assuming that they will have the most computational effort put into these corresponding chains, will basically lead into the final state of the chain. So this is basically going back to the properties of the blockchain. The persistency aspect will be taking several minutes, basically, as it is. Nevertheless, I think it's a very important contribution because this allows to change the way how people can look into blockchains and ensuring large-scale distributed system. And for that, we have seen a lot of innovation, starting with the second generation, which is Ethereum, where at the beginning, Ethereum was also following the path of proof of work, which meant that you are, again, still computing this expensive hash. And later on, actually, Ethereum switched into the proof of stake system. But coming one step back, basically what was one of the main advantage or novelty of Ethereum was that they have realized that Bitcoin is great for the use cases of actually being immutable blockchain, but it's providing limitations when it comes to actually use cases that can be adopted by Bitcoin because it doesn't have really any programmable capabilities, or it has some, but that are rather limited. And Ethereum, together with Vitaly Buterin and Gavin Wood and others that were around at that point in time, have seen it as a limitation, and they came up with the idea to actually offer a smart contract on top of Ethereum, which basically you can think of it like that instead of just exchanging information when it comes to sending a transaction with respect to the update of your account, for example, you can actually also do more complex operations and basically program your logic. It can, for example, be for the use cases of DeFi. You can do some auctions. You can also do many other activities basically that will be directly implemented on the blockchain. And it's providing or serving as a so-called blockchain computer where you have fully programmable environment that basically also leads to the aspect of, or calling it smart contract platform itself. And this also allows for composability, meaning that if I already deploy one application and I want to deploy another application, I don't have to fully rely only on the applications I do, but I can also rely on third-party applications that are already running on the chain. So that way, before I update the state in the system, I can actually run this logic that will be implemented in the smart contract itself. The motivation actually of shifting from proof of work to proof of stake, I think was already outlined in one of the early posts of Vitalik, but in blockchain system, one of the main challenges actually you have is so-called bootstrapping problem, where you actually have to firstly bring users and funds and adoption and build the ecosystem around the corresponding layer 1 blockchain, which of course is not an easy task. And from the historical reasons, we see that, for example, Bitcoin has done it very well. They have a really large number of pool providers, very large community and large valuation, which basically is allowing also to provide the security of the system. And this is also one of the reasons why Ethereum has followed this path, to basically make sure that they will have enough adoption. And later on, once there is enough liquidity in the system, that is basically ensuring also the security of the system, they switched to the proof of stake system as it is, which happened in the event so-called merge, where basically they changed to Ethereum 2.0, that is now a fully proof of stake system. Some of the aspects of the smart contracts, we don't have to dive into the details, but you can think of it that actually each of the individual hosts in the system is executing the smart contract in so-called virtual environment, where basically you are executing the logical updates that are run on top of the data you provide. And since we are talking about quasi-Turing complete language, you can write actually quite a variety and complex logic and functionality into the smart contract themselves. So, and very important part again, even for the smart contracts, we actually have this aspect of transparency, meaning that actually anyone can see the state updates. And also it's actually allowing for quite an advanced level of automation because the smart contracts are executed in an autonomous fashion. and they can basically behave also on behalf of the functionality of the programmers themselves. So one might ask now, why actually do we need third generation of blockchains, right? We already have this since Ethereum 2.0 when it comes to the aspects of functionality, right? Because at the end, the new blockchains that are being introduced are mainly focusing on being smart contract platforms. So why do we actually need the new generation? And the main answer to that is so-called blockchain dilemma, where we see that even systems like Bitcoin or Ethereum are suffering on that front, where we want to have a secure system, we want to also have a scalable system, and also decentralized system. And when it comes to Bitcoin and Ethereum, they mainly actually provide very secure, very decentralized, but not so scalable. What does it mean? That basically if you want to interact with the system and ensure its liveness, it's of course possible, but you are having limited capacity in the system on how many transactions per second you can operate at once. For that, there was a lot of motivation to basically make sure that the underlying layer 1 will be trying to, in some shape and form, solve this blockchain dilemma that basically states that only 2 out of these properties can be valid at once. But still, we see that each of the approaches may be sacrificing in different way. This is basically the part of the trilemma that only 2 out of these properties can be valid at the same time. So some of them maybe sacrifice decentralization, but they offer security and scalability, meaning that actually you can process more transactions in the system. Or actually, as we will also see in some of the talks later on today, even on Ethereum, they are trying to look into the aspect of scalability using so-called layer 2 solutions that aim to offer the scale to millions of transactions per second in the future. And the reason why we also have so many layer 1 solutions, I'm just providing some aspects of the design space here, which is, I think, from my point of view as a researcher, very interesting. We can actually consider many different parts that we have to design for in order to achieve secure, decentralized, and scalable system. So starting with some of the aspects of the security, we have to consider, since we are talking about the global distributed system, some aspects of the delay in the network. When it comes to, for example, having nodes in Europe, Asia, and US, of course, there will be some delay. How does this type of delay affect the performance of the system? What happens if some parts of the world become suddenly disconnected due to some bugs in the configuration of the, for example, some other network protocols, or even as a malicious action by different parties? What happens if some of the peers become non-responsive? Maybe they just had a bad time and or didn't pay their cloud account on time and they become no longer responsive. What if some of the peers are actually malicious? This is again going into the sense of the BFT. How do we ensure the system security under such type of conditions? On the other hand, we have the aspects of decentralization, right? Because of course, if we would just run it in a single location, several nodes running in a nicely cooled data center, we are actually able to achieve a very good throughput and still very good scalability of the system in that sense, but we are actually sacrificing on the centralization. So bringing this aspect also into the context of Bitcoin or Ethereum, we are talking about how is actually the stake distributed among individual peers. How is the mining power distributed among individual peers? On top of it, we of course have governance, so meaning like each blockchain itself has some form of governance where in order for the protocol to evolve, there actually are some people responsible for making sure, or community responsible for the voting on the changes on the chain. Is this governance centralized or operate in a more decentralized fashion? How does it work? Who can actually participate in the consensus itself? Do you need to have hashing power? So how expensive is to buy such a device? Do you need to have some stake? How easy is such stake accessible? And so on and so forth. The last one I will just briefly touch on is the other parameters, of course, like finality, which I will be briefly talking about. Again, aspects of throughput and also the aspects of forking that I mentioned can happen, so-called soft forking, where you have in Bitcoin basically multiple proposals at once. It basically results in this split view for a certain period of time until it again becomes persistent. So with all of this stuff in mind, we basically see a lot of design spend that basically led into many new L1s popping up that try to solve this blockchain dilemma. Just also to clarify, who can actually participate in the consensus, right? So we know that the consensus itself is ensuring the persistency, liveness, and safety of the protocol, but who can actually participate? And there's, I think, one misconception usually that many people consider that the proof of work or the POS, the proof of stake, actually corresponds to the consensus, which is actually not correct. It's basically the POS or proof of work or proof of stake is a so-called civil resistance mechanism, meaning that only if you have certain power, meaning computational power or certain stake, you are actually allowed to participate in the consensus, which is it's a big difference when it comes to the type of security assumptions when it comes to joining the system itself. General family of the civil resistance mechanisms focusing on proof of work is, of course, mainly used in Bitcoin. So in general, you are basically trying to solve some puzzles in order to participate in the consensus, which, as we know, is not very energy efficient. There are also some tendencies actually of doing some changes to the proof of work to make it maybe more, still maybe not as efficient, but at least the outcome of the work to make it useful. So there were some proposals, for example, on computation of some protein folding, which was quite interesting. And then we have a variety of proof of stake approaches, so that way maybe if you don't have enough stake, but you still want to participate in the system, you can delegate your stake to some peers in the system. You might also have to lock your stake for a certain period of time, or just basically as long as you have any stake, you're actually allowed to participate. So there are flavors of these mechanisms. I'll just briefly talk about it, just like a short overview. When it comes to Bitcoin or also Ethereum, we are usually talking about so-called Nakamoto-styled longest chain approaches. That one of the main innovations of Bitcoin was it's allowing this probabilistic finality, which is very good for scalability. Or you have this PPFT approach, which is basically coming from this traditional BFT protocols that is offering deterministic finality, but actually sacrifices in scalability. And for that, we also start to see sometimes hybrid approaches. For example, Ethereum 2.0 is actually combining the aspect of the longest chain with later on adding finality gadget on top of it in the context of PPFT or similar like pattern to basically achieve this deterministic finality. Overall, the main differences still persist the same, that the traditional BFT systems basically usually assume a fixed number of peers, whereas for the chain-based solution, we usually either subsample the number of peers or assume dynamic participation of peers joining and leaving the system. And just a last slide, a little bit teased at the beginning, how far are we from the mass adoption? So I don't have an answer to that. I just want to provide some, from my point of view, interesting stuff to consider. So I think first step is actually, can the blockchain itself allow running of thousands of distributed applications on top of it? The answer to that is yes. All of the current systems allow for deployment of many, many smart contracts, many applications on top of them. So that way, basically, people can just deploy whatever smart contract logic they have, and it's possible to deploy it. However, the issue when it comes to the scalability is usually how many interactions per second you can have with this type of smart contracts. And this becomes a bit tricky, considering into what type of blockchain we are looking into. But we start to see more and more interesting solutions when it comes to that, to basically allow the scalability to millions of transactions per second. We are not there yet, but hopefully in the next years we will see a lot of evolution in that sense, which also I think will be some aspect we'll be talking about when it comes to modular blockchains or so-called upchains. And the third step, which I think is also something we hopefully will are building up together, is to bring new users on board that will be actually using this type of systems and applications that will be developed and worked on by maybe some of you in the future, or also in the collaboration with university. So from my point of view, I definitely see a lot of interesting times ahead of us when it comes to research, development of new applications, and basically being the early adopters in the system. With that, I would like to thank you. And if you're interested in what we are doing at the university or try to follow up, I'll be here for the next 2 days and we'll be happy to have a chat with you. Thank you very much.